Hey guys, in this video I'll be going over the solution to Lasers Everywhere alternative from CodeChef March Long Challenge 2020. And a very important thing to note from the problem statement is that the given array is randomly generated. And that'll be very useful for us later on. I'll go over the solution to subtask 1 first, since it is a bit different from subtasks 2 and 3. In subtask 1, M is very small. We have 10 queries. We can ask at most 3 questions, and each query contains at least 1,000 points. Notice that we can't even ask 1 question per query because we only have 3 questions. So it prompts us to wonder if we even need to ask questions for this subtask. And then we notice that there are a lot of segments for each query. So if the array is randomly generated, then it means that probably at least one of them will have a height of n-1, which is the maximum possible height. So our solution is to output n-1 for each query. And it turns out that the solution will give you AC. And I'll prove that this solution has a very low probability of failure in the end. In subtasks 2 and 3, M is very big, and we have 10 queries, and we can ask at most 10 questions. And each query contains at least 100 points. Notice that since we have 10 questions, we can now ask 1 question per query. Our strategy, and we still have a lot of segments per query, so the randomness of the array will probably still be useful for us. So our strategy is to just hit as many segments as possible with the laser in the question. So a laser starting from x1 to x2 at height y, and we'll just hope that the laser will happen to hit the segment with the maximum height. So in order to hit as many segments as we can in the range from L to R, we should, for the question we ask, we should have x1 equal to L and x2 equal to R. And we can also, we now need to consider the choice of y. And if we choose, for example, y equals to 1, then this is a very bad choice because y equal to 1 is on the border. So all segments are very unlikely to intersect with the line y equals to 1. So it makes sense that we can intersect more segments if we choose y to be in the middle, which is n divided by 2. So our solution is to ask the question from L to R and at height m divided by 2 and output the answer for each question. And it turns out that the solution gives AC. So in the contest, you don't need to prove it, but I'll still include the proof that the solution will work in the end. So now I'll give the proof for subtask 1. So you have these segments here, but in our proof, we'll ignore every other segment. And this is because if we make the segments disjoint, then the probabilities for the segments are independent of each other. And then we can bound the probability of the failure by this expression here. So this 98 over 100 is the probability that a segment does not have a height of n-1. And this is for m equals to 10. And then we take this to the power of the number of segments that we have, which is r minus L divided by 2. And we divide by 2 since we ignore every other segment. Okay, so you might wonder where this 98 over 100 comes from. And this is because we have n possibilities for each point. So that means you have n squared possibilities for each segment. And then for a segment, there are two possibilities for it to have a height of n minus 1. We can either have 1m, or the segment can be m1. And these two are the only cases when the segment will have a height of n minus 1. So in order to find the probability that the segment does not have a height of n minus 1, we take 1 minus 2 over n squared, and for m equals to 10, it turns out to be 98 over 100. So lastly, if we calculate the expression, if we plug in the numbers here, we'll find that the probability of failure is very, very small. So this explains why the solution works. And now I'll give the proof for subtasks 2 and 3. So because we take the line at y equals, we simply take the answer for the question and output it as the answer for the query. It works if our line at y equals to m divided by 2 intersects the maximum segment. And notice that any segment with height greater than m divided by 2 will intersect the line y equals to m divided by 2. So, for example, if this segment has a height greater than m divided by 2, then no matter where we move it, it has to intersect the line in the middle. So now we want to prove that the maximum segment will have a height greater than m divided by 2, because if the maximum segment has a height greater than m divided by 2, it means that the maximum segment will intersect the line in our question. So again, like in subtask 1, you'll ignore every other segment so that the probabilities for the segments are independent of each other. And we can bound the probability of failure by this expression here. So P is the probability that a segment has a height smaller than m divided by 2, and then the exponent is just the number of segments that we're considering. And now we need to calculate what P is. So if we have a segment which has, for the first point, it has a height of A, and the second point, it has height of B. And if we divide A and B by n, then we get this, we know that A and B has to be between 0 and 1. And also, because the height is smaller than m divided by 2, the absolute difference between A and B should be less than 1/2. And to find the probability that this happens, we can use geometric probability. So basically, if we view the x-axis as A and the y-axis as B, then this condition here is basically means we're looking at the points in the blue square. So A can be from 0 to 1, and B can also be from 0 to 1. And then the red region represents the pairs such that the absolute difference is less than 1/2. So we want the probability that if a point is chosen inside the square, what's the probability that it will be inside the red region? And then we can do some simple geometry to find the area of the red region inside the blue square. And basically you can subtract these two triangles, and each triangle is 1/8. So the two triangles added up together has an area of 1/4. So then if you subtract the two triangles from the area of the blue square, then the area of this red region here is 3/4. So that's our probability. Yeah, so now that we have P, we can evaluate our expression. And it turns out that it is a very, very small number. So the solution works. If this video was helpful for you, then feel free to like and subscribe. And if you have any questions, then feel free to ask them in the comment section below. Thanks for watching.